Hello, my name is Isabel Fitton and I'll be introducing Watch This. Observational learning in VR promotes better file transfer than active learning for a fine psychomotor task. This project was completed at the University of Bath in collaboration with PwC. Virtual reality is increasingly being used to teach people new skills in the workplace by immersing them in realistic training environments. Approximately 78% of industrial VR training use cases involve psychomotor skills, i.e. skilled movements that require coordinated motor action and cognition. For example, manual tasks that involve learning a procedure or sequence of actions that require the user to grasp and manipulate objects, operate equipment, and/or use tools. One of the advantages of VR training is that it offers a platform for learning by doing, also known as active learning, and therefore most applications give users a first-person perspective VR experience that guides them to complete each step of the procedure using visual prompts and/or written or verbal instructions, allowing them to learn the skill through rehearsal. This type of training has been shown to be effective for training manual, also known as fine psychomotor skills. However, real-world training where an individual is shown how to complete the task and allowed to practice produces superior results. Observational learning, or learning by watching, is an effective and commonly used approach for acquiring fine and gross, i.e. full-body, psychomotor skills outside of VR, which has been shown to provide equivalent outcomes to active learning whilst offering potential benefits of time efficiency and reduced cognitive load. In particular, combining observational learning and physical practice is thought to be one of the most efficient and effective approaches to real-world training. Today, observational learning has been relatively underexplored in VR, with most examples focusing on gross psychomotor skills such as sports. It is unclear whether observational learning combined with practice is effective for learning fine psychomotor skills in VR, or how this compares to active learning in VR. Therefore, in this research, we pose research question 1. We seek to understand how active learning compares to observational learning of a fine psychomotor task in VR. To effectively compare different learning approaches in VR, it is important to assess if the skill transfers to the real world. Skill transfer in VR is commonly assessed using near-transfer tasks, where the real-world task is identical to the one experienced in VR. However, far transfer, where the taught skills are applied in a different real-world context, is rarely measured. Therefore, we pose RQ2, to investigate how active learning compares to observational learning when transferring skills to the real world, using both near and far transfer tests. How to implement observational learning in VR remains an open question. Observational learning theories predict that model similarity impacts learning effectiveness, possibly because the action-observation network fires more as the similarity between ourselves and the model we are watching increases. The highest degree of model similarity is achieved using a self-model, and prior work has demonstrated that video self-modelling can be used to enhance fine psychomotor skills, such as in a cup stacking task or playing a video game. Existing research into whether this phenomenon occurs using avatars in VR has shown that learning is more effective when the avatar demonstrator is made to look increasingly similar to the user, either by matching the skin tone, hair colour and gender in Fitton et al., or by using a photorealistic avatar in Frank et al. However, this has only been shown in the context of gross psychomotor skills such as dance or squats. Understanding whether the self-model avatars are as beneficial for learning fine psychomotor skills and have the same advantages as video self-models is an important design consideration for a wide range of VR training applications that could utilise the observational learning paradigm. Therefore, in this research we pose RQ3. We investigate how demonstrator similarity affects observational learning of a fine psychomotor task. In a between-subject design, we compare active learning and observational learning from a dissimilar, minimally customised or fully customised self-avatar demonstrator. Participants were tasked with learning to assemble the 6-piece interlocking 3D puzzle known as a Burr puzzle that's shown on the screen, We chose this task because it has been used in prior research into VR training of manual tasks and represents a fine psychomotor skill with procedural elements. Each participant attended 3 lab sessions. In the first, they answered preliminary questionnaires which allowed us to balance the groups and had their photograph taken, which was used to produce their self-avatar. In the second session, participants completed a VR familiarization task, the VR training, questionnaires, and the immediate retention and transfer tests. We used insights gained from interviews conducted with industry stakeholders who have experience designing, developing, delivering, or using workplace VR training to inform the design of the VR training in our study. So please check out our full paper if you're interested in these findings. The VR training was repeated for a total of 40 minutes up to a maximum of 10 trials. Each trial involved 2 parts, training and practice. The training was either active or observational depending on the condition the participant was allocated to. The final session took place 10 to 14 days later to study skill decay. In this session, participants completed questionnaires and the retention, near and far transfer tests again. For the active training condition, in the VR training part of each trial, participants were guided how to complete the puzzle with text prompts and animations, as you can see here. Those in the observational condition watched the demonstrator avatar complete the burr puzzle twice instead. Participants in the self-observational learning condition observed the avatar created from their photograph. Minimal and dissimilar avatars were created using AI-generated photographs and a default body shape. Those in the minimal condition observed an avatar that matched the gender, skin tone, hair colour and age they had selected, whereas those in the dissimilar condition observed an avatar that had a contrasting skin tone and hair colour and the gender and age the participant identified with the least. For all conditions, the practice phase of each trial consisted of the same hands-on practice. Participants were given a maximum of 180 seconds to assemble the puzzle, and we recorded the number of pieces assembled correctly and the time taken. Red and green highlighting around the pieces indicated whether participants were making a mistake. At the end of Session 2 and Session 3, participants completed the questionnaire measures, the retention, near transfer and far transfer tests. Each test required participants to assemble the same burr puzzle that they had been trained to complete from memory within 3 minutes. The retention test took place in VR, while the transfer tests were conducted in the real world using 3D printed puzzle pieces. For the near transfer test, the colour coding and starting orientation matched the VR training. For the far transfer test, the colour coding was removed and the blocks were positioned differently. Participants were also asked to complete a tone counting exercise at the same time to mimic real-world distraction. Our findings demonstrate that VR training was successful for learning an assembly task, with the majority of participants able to complete the puzzle in the VR retention test after the training. Whilst existing VR training applications almost exclusively use active learning, our results demonstrate that observational learning combined with practice is highly effective as a learning approach in VR. Both groups practiced assembling the puzzle in the practice phases, but only the active group assembled the puzzle during the training phases. Despite this, we were unable to detect significant differences between the active and the observational conditions, indicating a functional equivalence between action and observation. Similarly, we found no significant differences between active and observational learning for transferring skills to the real world when the task is exactly the same, i.e. in the near transfer test. However, observational learning significantly improves the ability of users to transfer their learning to real-world tasks beyond the context learned in VR when compared with active learning. The odds of succeeding in the far transfer test were between 6.6 and 7.9 times higher for those in the observational learning condition compared to those in the active condition, with a large effect size observed for each of the individual observation conditions. This phenomenon has also been demonstrated outside of VR, indicating that observing contributes to learning in a way that allows the individual to apply their skills more easily to variations of a task. In line with prior work, our results show significant skill decay across all conditions after a 10 to 14 day delay between training and performing the tests. Only 34% of participants were able to completely assemble the puzzle in the delayed VR retention test, representing an almost 50% drop in success rates. Significant decay was also observed in the near transfer tasks. Far transfer success rates fell after 10 to 14 days, but not significantly. This is likely because the immediate success rates were much lower on this task. In contrast to prior work, we find no significant effects of avatar similarity on learning, and it is likely that only small effects exist. However, qualitative insights reveal that using fully customized, more realistic representations of the user in observational learning was more likely to produce uncanny valley and novelty effects, which can distract the user and prevent them from focusing on learning the fine psychomotor task. To conclude, observational learning in VR can be effective when combined with hands-on practice. It also yields significantly better results in real-world far transfer tasks and should therefore be integrated into VR training applications. However, avatar similarity does not appear to increase the learning of fine psychomotor tasks, and therefore self-similar avatars may not be useful in this context. Finally, learning in VR decays over time independent of learning approach. This reiterates the importance of repeating training and not allowing long periods of time to pass between being trained virtually and utilising the skill. We also emphasise and encourage the use of both near and far transfer tests for assessing VR training effectiveness. Thank you for listening. Please read our paper for further details.